So, I want to welcome Ryan Pohlig back again. I know many of you were here last year. He gave a really great presentation about this. And so, he's from University of Delaware, statistician, graduate of the University of Delaware. And so he's going to give us a talk today on a really, really interesting topic, very fascinating, structural equation model for SEM also. And then I believe next week we'll have a follow-up on that as well. So, Ryan?
When Paul said if you have technical questions, use the chat feature, he meant technology questions. Technical questions I can't answer. So here's the sort of famous quote by George Box, which is pretty apt today as I'm going to be talking a lot about modeling. And it's the idea that at some point every model will break down. But what we try and get is the most useful one we can find at the time. So typically I give these presentations to psychology and other behavioral type fields. So the opening line is sort of cut and pasted from that, and then I felt, well, now I'm presenting at a hospital, so I got to add a little bit. So I feel like SEM's also growing in the medical fields, and you can just do a quick PubMed search, and you'll find structural equation yields 10,000 results. But if you restrict it to just the last 5 years, you get 5,000. So clearly it's been picked up and it's being used a little bit more. So structural equation modeling, SEM, covariant structure analysis, causal modeling, latent variable modeling, it's all sort of relating to the same idea. That's, we want to measure things that you can't see. That's one of the reasons it's really popular. Outside of just looking at relationships of observed items, you can also get that of unobserved or latent variables. You can use SEM in all types of research designs. It used to be thought that it would not be good for experimental designs, but sort of more recent uses have eliminated that restriction. You can also get direct and indirect effects very easily. And you'll know through regression modeling, getting an indirect effect can be a pain. So what I'm talking about is a direct effect is when one variable directly predicts or impacts another one, which is like a relationship from A to B. And an indirect effect goes through a set of variables or another variable. And in this case, the indirect effect of A on B goes through C and D. So classically, structural equation modeling was sort of known as a confirmatory technique. And that is because you have to specify a model before you can do the data analysis. And so therefore, the thinking was that it can only confirm things. Sort of more recently, people have been talking about moving it towards the exploratory phase. There's an 09 article that's sort of famous that pushed it that way. And then next week, you'll hear from a colleague of mine at the University of Delaware about a special type of SEM called partial least squares, which is essentially only used for exploratory type analyses. So where did SEM come from? Its sort of roots come from three different fields. The first is psychometrics. The idea of trying to get at an unobserved phenomenon that's causing score values to be seen goes back to exploratory factor analysis, which sort of go back to the turn of last century, Spearman. Then Euroskog in 1967 establishes a way to use maximum likelihood in a discrepancy function. He then came up with confirmatory factor analysis, which is slightly different than exploratory. Now you're specifying ahead of time how many different latent variables there are and which items load on which. Sewell Wright had what people call the first true SEM model in his idea of path analysis, which he introduced in 1918. And this is testing the relationships just of observed values at this time. And lastly, there's pieces from econometrics and simultaneous equation solving systems of simultaneous equations. And so that really goes back to, I'm not going to put yours in, and the Cowles Commission. Then in 73, you'll recognize the name Eurosky again, sort of became the grandfather field. In these three papers, they sort of combined these into one framework, and he sort of took the lead as well as establishing one of the first softwares. So he sort of became the grandfather of the technique. In 79, Bentler and Weeks further generalized the model, and I'll talk briefly about that when I get to it. And it turns out that almost all the statistics you run are actually just special cases of SEM. Right? That's what, when people come out with new equations, they love to tell you, well, you're really just doing what I have proposed, right? It's just a special case, so mine trumps yours. It's always the one up. So what's actually in SEM? Well, what we typically call SEM are sort of the more advanced models. We don't really talk about regression modeling and t-tests as SEM, even though they technically, mathematically are special instances. So the three foundation methods are path analysis, which uses only observed variables, confirmatory factor analysis, which is sort of a psychometric test. That is, we're interested in measuring the latent variable and getting the estimates of sort of how the observed items relate to that. Then you have a full SEM model, which sort of combines the path analysis and the confirmatory factor analysis. So now we're looking at latent variables and the relationships between them. Then it went one step further, and we have multi-sample or multi-group SEM. That is, the model can be different between the two groups and can be tested to see if individual pathways are different between the two. Sort of a special case is what's called a mimic model. It's a multiple indicator, multiple causes, and this is sort of a way to use dummy coding in SEM. Then it was sort of further established to including means, so MAX is mean and covariance analysis. I won't be talking much about this. It just really complicates the formula for an intro session on this. Multi-level SEM, right? Everybody's talking about mixed models now. SEM generalizes to that. Latent growth curve modeling is really a hot topic sort of in the past couple of years. There's sort of two main methods, the factor of curves and the curve of factors methods. I'm not going to actually be talking about them, but your nomenclature. There's sort of the two main ways of looking at latent growth curve modeling. You have latent class analysis, which is like cluster analysis, but with latent variables. Then you have mixture modeling, which is like the latent class analysis plus the latent growth. And the special instance of this is the latent trajectory analysis, which is also sort of garnering more use. So why does SEM matter? Or why should we use it? So here's the interactive portion of today's lecture. So what are the assumptions for typical regression analysis?
Independence.
Independence.
Normality.
Normality of the residuals. I hope you guys aren't using these models. What else should you test for, I should say?
Homoscedasticity.
Right, equal scatter. Nobody else? Should be happy you all graduated, right? So the four main ones people normally can come up with are normality, linearity, homoscedasticity, and multiclinearity. So I applaud Claudia for coming up with two of the other ones that are not as mentioned as often, which is independence, typically of subjects, right? It could be measurement occasions. And variables should be interval or ratio level, and then sort of you can get around that using the ANOVA framework in the general linear model when you have grouping variables that are nominal. But when we look at this, you can test for normality, and if you violate that, right, you can use a transformation or generalized model. In linearity, you can model those nonlinear terms. In homoscedasticity, if you violate that, you can use weighted least squares or an adjustment to get corrected standard errors. In multiclinearity, this actually goes back to something Paul presented at the very first one of these. That is, you can use a principal component analysis or a ridge regression. So there's one more sort of assumption, and almost nobody ever talks about it. Does anybody have a guess? You guys are worse than most classes. And that is, variables are measured perfectly. Right? They have perfect reliability. What happens when you have imperfect reliability, especially in a multiple regression analysis? Well, it turns out you can commit both type 1 and type 2 errors, which sounds a little backwards. It turns out when you have a very reliable item, you can end up committing type 1 errors and type 2 errors with very unreliable items. And what happens is the unreliable items are not accounting for as much variance as they should be. So the very reliable ones tend to eat up that extra variance that should have been accounted for by other ones. And that's sort of how you get you can commit both type 1 and type 2 errors. Yes?
But there's hardly any outcome that's not measured without error.
Yes, right? So that's one of the ideas of why SCM should be so important. And I'll get that. So I don't know how many people have had actual test theory or talking about error. I know Paul and I have sort of a different background for statisticians. We come from education. So this is actually sort of a component of our background. According to classical test theory, any observed item is a combination of the true score plus error. And we can model this sort of using a regular regression equation. And here I have to apologize for the slides. I had originally created them on my MacBook, and then in PowerPoint, by the way, and then I brought them into my work computer, which is Windows, and all the equation editor must be different. So I had to redo all the equations earlier this week, and instead of actually highlighting each individual symbol for vectors and matrices to bold them, I just bolded the whole equation at the same time. So you'll wonder why some of the subscripts and stuff are bolded, and that's just because I was being busy. So when we talk about this regression equation, we have a true score, which you never really see, because you're always going to have some type of error. And it turns out if you standardize X, you can get what's called factor loadings, which are the regression coefficients, which is sort of a way of scaling the true score. We can't directly observe the true score, so reliability for a single item doesn't really exist. Now, there are ways of getting around that, using multiple items, sort of collapsing across them, getting averages or sums or subtotals. What we typically refer to as reliability is the portion of variability that's due to the true score alone. So as I said before, we can talk about the loading in a factor analysis. And it turns out if you square the loading, that's actually the reliability. But since we don't know the true score, we can't actually get that coefficient using a regular regression analysis. So how often in practice do you actually measure an item that's perfectly reliable? And never, right? And there used to be the one example of sex and gender, right? And I feel like since I started undergrad to now, people have finally realized that that's not true either.
Death, I think you can measure without error.
Yeah, until you consider people in comas, right?
99%. Most of it.
So how can you get around this? Well, you can start loading up on items that measure the same thing to get a more reliable measure. But what happens in regression analysis when you do that? Think back to those assumptions that we had. And one of them was multicollinearity or singularity, right? So now I'm telling you, you can't measure the outcome well or the individual variables well, and you need multiple items. But you can't use multiple items. So how can we measure that true score without the error measurement? And that's the idea of a latent variable. That's a construct that's not directly measurable, but it can be indirectly assessed through observed items. And so, for instance, here, I have just pictured 3 variables, x1, 2, 3, and you can imagine that each of these circles represents the variability of the items. Any overlap indicates sort of a correlation between them. Now, if x1, x2, and x3 are all measuring the same underlying construct, we can see that there's a large portion of shared variance among all 3. And ignore the Greek symbols I for now. So how do you measure these latent variables? Well, I already sort of talked about exploratory factor analysis, which, if most statistics programs are similar, that's about as far as you get. So you probably are sort of familiar with this, but I'll run through it real quickly. The goal of an exploratory factor analysis is to measure the underlying construct using observed items. We're saying that the variables are correlated because that underlying construct is causing their scores. And that idea of causality going in that direction is sort of important. Typically, we hypothesize a smaller number of latent variables than observed items, because technically you can have a true score on every item, right, which is a latent variable for every item. But what we're trying to say is that these items are somehow related, and so they're all getting at one construct. In exploratory factor analysis, we don't hypothesize which items load on which latent variables. And the equation that ends up coming out of the exploratory factor analysis is a linear combination of the latent traits and the errors, which, if you think back to our measurement model from classical test theory, is exactly what it was shown. So if you recall, again, Paul's talk way back, that was a while ago, it was in September a year, so almost a year and a half ago. You might be saying this exploratory factor analysis sounds really familiar. And in fact, the math behind it is almost equivalent to principal component analysis, but there are slight differences. The first is in PCA, the principal component analysis, we don't care why variables are related. We just care that they are related because we're trying to reduce the data set. The components are technically just aggregates of score values, whereas exploratory factor analysis, we're saying that the underlying construct is causing the scores. Some other slight differences. Typically in PCA, you don't let the factors or latent variables themselves correlate, which you can in exploratory factor analysis. And also in EFA, you typically apply a rotation to try to simplify what's going on, and that is you maximize the amount of variance accounted for by the fewest number of latent variables. It's supposed to make things more interpretable. So here's sort of a technical definition of what SEM is. It's a multivariate analysis concerned with representing population moments based on a smaller number of parameters that are hypothesized based on some theory. Conceptually, what we're doing is we're taking factor analysis and merging it with regression. There's actually 3 types of latent variables. I've only introduced you to the first one. Indirectly, I've introduced you to the second one, which is errors of measurement. Also, there's a third type, which is the unmeasured residual variables. In SEM, you can actually model all 3 of these types, which is why I'm giving it to you now. So the huge advantage of SEM is you can get estimates of relationships measurement error-free. So what's the goal of SEM? What's the goal of most analyses, especially when they're model-based? Well, what you want to do is have your model reproduce the relationships you've seen in your data. So in statistics, what's the thing that we use to show the relationships among variables? It's the covariance matrix. And you'll see here that I've now defined sigma as a population covariance matrix, which we can never actually measure, right, unless you get access to the whole population. So what you do is you take a sample, and you get the sample one, and hope that that's an unbiased estimate. So that's S. So what we're really trying to do is build a model that reproduces the covariance matrix seen. And in this case, the model implied covariance matrix is sigma theta, theta being the generic use for a parameter estimate. And of course, we always state our null hypothesis in terms of population parameters. So that's why that second bullet there. But what we're really doing is we're testing to see if our model can reproduce the covariance matrix seen in our data. I do talk a little fast, so if you have questions, just raise your hand or shout out. Given this idea of trying to reproduce the covariance matrix, there's sort of two different types of research questions that structural equation models ask and answer. The first is, does this model fit? That is it doing a good job of reproducing the covariance matrix? You know, if your theory is good and the data matches that, it's a good fit. Given that it fits well, you can now actually test every single parameter in the model. And then down here, the typical one is the parameter different from 0? But you can also ask is if the parameter is different from some other value, right? Typical null hypotheses. There are three sort of components of SEM. This is more for didactic purposes than anybody actually applies these in this sort of way. The first is the structural model, sometimes called the path model. It's a visual representation of your model at the higher level. That is, the relationships among the latent variables. Typically, we use a path diagram. I'll get to that in a minute. In this sort of component, we're also looking at the different effects. That is, the direct and indirect effects. The second part is the measurement component, and that's relating the observed variables to whatever hypothesized latent ones you have. And last one is trying to estimate it. Maximum likelihood is the most common method. There are a number of different sort of adjustments to try and help with some of the shortcomings. And there's actually one method that has no distributional assumption. The problem is you need really large n for it. So just two slides real quick on the background before I actually get into the method. It's what I would call a large sample method. And sort of Klein recommends a 20-to-1 sample size to parameter ratio. In regression, people often use the 5 and 10 rule, right? So this is sort of double that. Also, it's not recommended to go less than 5-to-1. Power analysis can be done. So Kim is my dissertation advisor, and he sort of has the method for it. And he's never seen it applied correctly. So I would sort of stay away from trying to do it. Here's some quick terminology that I'm going to sort of be mentioning throughout the lecture, the rest of this little lecture. Exogenous and endogenous variables come from econometrics. An exogenous variable is never predicted. An endogenous variable is an outcome at some point. Disturbance is the error term for the endogenous latent variables. And of course, being statistics, right, we have to throw everybody off. So recursive and non-recursive have opposite meanings in SEM from what you typically think. And I've never gotten a satisfactory reason on why. When I actually show you the models, we'll be talking about what's called the symbolism in the RAM, which is particular action modeling. The reason I sort of like this representation is everything that you'll see is estimated and tested, and almost everything that's estimated and tested will be seen. There's sort of one little difference. Lastly, standardized estimates are almost always reported. So you can think of them in terms of standardized regression coefficients. There's 4 major stat softwares, AMOS, EQS, Lizrel, and M+. They all have pluses and minuses. AMOS was sort of took the lead on bootstrapping methods. Turns out you can't necessarily use regular bootstrapping in SEM. You have to do something called a Bolenstein bootstrap. And Arbuckle was sort of the first to embrace that. It's also really easily embedded within SPSS. You can actually open sort of the files through each other, you know, SPSS files and AMOS, and vice versa. EQS is Bentler's software. It's good for estimating higher order moments using elliptical theory. And it actually has a very nice way of doing a model where you don't have to understand any of the math behind it. You can literally draw the model and it will test it. AMOS also has this features. It's just not nearly as easy to work as EQSs. Lizrel I've never actually used, so I won't comment one way or the other on that.
I have.
I do know it's sort of a pain.
It is.
Yes.
It was the very first one that really did.
Mm-hmm.
At the end.
And then lastly, M+, which is actually a really good general sort of software. It's great for categorical data, and when I use categorical data for right now, I'm talking about what you typically think of as nominal. Because, of course, in SEM, categorical data refers to what other people call ordinal. It's great for mixed modeling. It has a quasi-maximum likelihood. I will have to say, if you're using syntax, M+ is very user-friendly compared to, say, EQS or AMIS. Of course, all the softwares are all updated. For almost all the analysis, they'll all reproduce the same results. There are some minor things that are different between the two. EQS is right now the only one that lets you do the higher order moments. M+ lets you do QML. I don't know if Lizrel lets you do QML or not, but you can't in EQS. You can also use SAS, ProcCalus, and TCalus, which are burdensome and not easy to use. I would recommend against it. And R is sort of getting better with some of the packages. In fact, EQS and M+ have sort of embraced R, and it's easy to go from one to the other. So now let's actually talk about some of the math behind it. And so, as normal happens, we have to talk about some notation first. And sort of Urskog, Kiesling, Wiley, which are those three people I talked about, sort of introduced the concept, came up with what's now called Lizrel notation after the software program. And it's linear structural relations is what Lizrel means. And we're going to use three equations. So now SEM is three equations. Two are measurement, and that is going from the observed variables to the latent variables. That's what we're trying to model. And then the third, the structural component, is the relationships among those higher order, sort of the higher level, that is among the latent variables themselves. Ventler-Weeks notation combines all three of these into a supramatrix notation. I'm not going through that because it makes all the math and stuff that much harder to show. So here is the slide that will help you interpret what's going on in lots of these models. And it's actually a lot simpler than this. I just put this up as sort of a reference. Observed variables are squares or rectangles. Latent variables are ovals. Errors are often not shown, but otherwise they're a small circle. Regression coefficients, whether they're a loading or a regression itself, is a one-headed arrow. Correlation is a two-headed arrow. And so here is an example of a structural equation modeling that I used in my dissertation. And you'll see here, if you ignore the hashed latent variable in the middle, we have sort of a very basic SEM model. We have three latent variables, two exogenous, xi1 and xi2, and one endogenous, which is eta 1. So you'll see that eta is a latent variable that's predicted by the other two, which is why it's endogenous. The other two are not predicted by anything, therefore they're exogenous. I've allowed, in this picture, xi1 and xi2 to be correlated. You'll see the two-headed arrow between there. Because this has long since been relevant to the field, right? My dissertation could be on something so similar, so I had to use an interaction effect. So what I would look at, that's what that hashed circle looks for. Other times it can be represented by a small black dot. So now let's talk about the actual equations. So there's two in the measurement components, and I apologize, this is probably the boring part of the presentation. One for the relationships between observed item and exogenous variables, and one for relationship of observed items and endogenous variables. And you'll see that they're set up almost the exact same, and it looks exactly like the measurement model from classical test theory. There's also two covariance matrices associated with these, and it's just for the error terms. Here's the structural component. This is sort of the one that's mostly of interest when you're doing SEM modeling. And you can see here there's one little hiccup from the regular regression model. And that is eta appears on both sides of the equation. Because it's an endogenous variable, it can also be used not just to be predicted, but can predict something else itself. So therefore, it's on both sides of the equal sign. Of course, there are two sort of covariance matrices. One is the covariance matrix for the x's, and the other one is for the error terms. So if you think about the covariance matrix of your data, if you just stacked all your variables, all your x's, and all your y's, right? It's a square matrix, so all your x's, all your y's are the same going up and down, x's and y's. You can think about breaking that up into 4 components. The covariance just between the x's, covariance with the y with the x's, the x with the y's, and the y with the y's. And you'd say, why would you ever do that? Well, it turns out, given some assumptions, and here they are, it's essentially saying the expected values of error terms are zeros. Errors shouldn't be related with other components. Sort of typical standard regression type assumptions. So it turns out that each of those submatrices, can be reproduced given those model equations. So of course, if you're going to test a model, you need to know your degrees of freedom. And now what I'm going to talk about is your model degrees of freedom, which is different than your sample degrees of freedom, which is the typical n minus covered parameters. In SEM, the number of parameters estimate are the non-redundant elements in these vectors and matrices. It's essentially everything that you're estimating. And that has to be greater than the number of unique elements in the covariance matrix of all your data. So like the upper triangle plus what's on the diagonal. Those are the unique elements in a covariance matrix. If there's less parameters than however many make up that. Models called just identified if they have the same number. Over identified if you actually can't test that model, that is if there's too many estimates for degrees of freedom. And under identified if it's a model that's estimable. Your parameters in SEM are typically either freely estimated, fixed to a value, or constrained to be a function of other values in the model. Now we'll talk about the estimation procedures. We'll go back. So there's your null hypothesis, which is actually assessed by testing whether the model-created covariance matrix is equal to your sample one. And it turns out all of these different sort of chi-square tests of fit can be put in one generic framework. That's the generalized least squares. And you'll see it's sort of your typical sandwich estimator with a weight matrix in the middle. So vector H is a little different than a vector command, and this creates a vector of unique elements instead of just a vector of what's in a matrix. You're simply changing the weight matrix to change different types of ways of estimating things. So if it's an identity matrix, you have unweighted least squares. If it turns out you're using inverse of the sample covariance matrix, you have weighted least squares. The most popular one is the ML. It turns out that the weight matrix is way more complicated. It's Conacher multiplication and stuff, so I didn't think that was worth putting up here. So I'll just put you what it works out to be. And it turns out that this equation is actually very similar and almost identical to the one Eurosky came up with for experimental factor analysis using maximum likelihood methods. So here are just some properties of ML in general. Could be biased in small samples, but asymptotically they're unbiased. The errors are consistent. They're efficient, that is, there's small asymptotic variance. The distribution of parameter estimates is typically normal, and it's scale invariant. So there's sort of some other reasons why you might want to use the maximum likelihood method. For all these different fit functions, the model chi-square value approximate a central one if the null hypothesis is true. That is, if the model fits you're not going to reject. So it's sort of backwards thinking of what you're used to doing in the rest of statistics. If your model works, you're not rejecting now. And of course, it follows a non-central chi-square if your null hypothesis is false or your model doesn't fit. And it turns out the fit function is a nice chi-square distribution with n minus 1 times, if you'll recall, the f is just the result of that sandwich estimator for the generalized least squares. Unfortunately, of course, right, chi-square tests can be biased. So mostly by large sample sizes. Look back, part of it is the n minus 1. So the larger your sample, the more likely you're going to find it not significant, which means that your model does not fit. So people have suggested all sorts of adjustments. Santoro and Bentler have a scale chi-score. Said that backwards, right? A scale chi-square value. There's the asymptotic distribution free method, which requires no assumptions. The problem with that is the weight matrix has to be really, really large. Of course, instead of trying to just fix the chi-square tests, there are other ways to estimate fit. And so people have come up with all sorts of different fit indices. And the idea is you want to look at how much variation there is between the observed sample covariance matrix and your model implied. Broadly speaking, they can be grouped into either incremental fit or absolute fit. Absolute fit look at how well the model reproduces the covariance matrix. That is, how well does this model fit compared to one that would be perfect? Incrementals say, how well does this model fit compared to one that is either slightly better or slightly worse? So there are some references if you want to look up the performance of lots of different fit indices. Turns out that Hugh and Bentler did a study where they looked at the relationship among the fit indices, and it turns out not all of them are highly correlated. Meaning some can imply a good fit, and some can imply a bad fit for the same model. They sort of came up with what their finding was that these three measure something different. That's the comparative fit index, the RMSEA root mean square error approximation, and the SRMR standardized root mean square error. It turns out that most people just report some of each. That's sort of the best way to go about it. Conceptually, CFI is sort of thought of as the proportion of relationships among the variables explained by the model. The RMSEA sort of looks at things as how much quality you get for a degree of freedom, as how well you're doing per degree of freedom. And the SRMR is sort of more of a global measure. See how well reproduced is the model as a whole. So what if your model doesn't fit? Well, of course, there are ways to modify your model to increase fit. This sort of goes against that theory and confirmatory type technique that I mentioned at the beginning. Part of the problem is you may add a pathway, or the test may suggest adding a pathway that makes no conceptual sense, right? But it increases model fit. Most of the time, model modification does one of two things. You're either going to estimate a parameter you were not estimating before, or you're going to take one that you were estimating before and fix it to a certain value so you don't have to estimate that anymore. One increases parsimony, right? One increases how well it's going to fit. Of course, right, here's the question that nobody wants to answer if your model doesn't fit. Typically what's done is we add all significant pathways first before we try and remove non-significant ones. There are 3 methods of doing these, and the softwares will do these tests for you, so it becomes really easy to modify your model. It turns out all 3 methods are actually asymptotically equivalent anyway. Now, how about individual parameters? Well, remember those z-tests you learned about and then never used again? Well, they're back. So what we have here is a simple z-test. It's a parameter minus a hypothesized null value over the square root of some sort of error. In this case, you're getting the error from the asymptotic covariance matrix, which is obtained from the Fisher information matrix. You can also test indirect effects. Right? And I said before, an indirect effect is an effect of one variable on another through one or a set of different variables. A total effect can also be tested. That is the sum of all the indirect effects and the direct effects. So if you'll think about how you would do mediation in regression, typically people use the Barron-Kenny method, right? That's 4 steps to look at one mediator, right? Whereas structural equation, you can do this all in one model, all at the same time. In fact, model modification may suggest mediation where you had not thought previously. The mediation itself can also be embedded in a larger model. And of course, just like the z-test for the actual parameter estimates, you simply need to find that error term for the indirect and total effects. Well, you get those from the asymptotic covariance matrix too. So it's quite easy in SCM to test the direct and the indirect effects. Of course, an individual indirect effect is a multiplication of all the direct effects leading up to that pathway. And I'll talk about that in a second. So here is an example of, I think this was just presented at the PT conference. And you'll see here, what we wanted to model was performance, self-efficacy, activity, and participation in stroke survivors. So this is a path analysis. There's no latent variables here. These were all observed. And you'll see here the hypothesis is that your performance will not only impact your activity and your participation, but it will also increase or decrease your self-efficacy, which can also increase and decrease your activity and participation. So what would be the point of looking at this? Well, PTs typically only look at increasing performance, right? They're now sort of coming into the psychosocial realm of looking at how to impact self-efficacy. But is it even worth looking at self-efficacy? And it turns out that this mediated pathway is significant, as well as the other mediated pathways. Now, you could not test this model in regression because there are 2 simultaneous outcomes. All right? So there's another way SEM is slightly more flexible than typical regression. So here is, this is unpublished, so I can't give you too much background info. The researchers were looking at the relationship between support, stressors, coping, and its impact on anxiety and depression scale. You'll see above that they're adjusting for race. Support is a latent factor measured by 2 items, family support and maternal support. Coping was a scale that had 5 subscales: acting out, partying, internalizing, prosociality, and expressing. And then you can see the stressors down below. That is sort of a stress factor of physical abuse, emotional abuse, sexual abuse, family stress, and then whether each of your parents were incarcerated. Now, I did not put factor loadings on here because then there's just too many numbers and it gets really confusing to try and look at anything. You can see here that the hypothesis is that support and stressors will impact anxiety and depression, but that potentially coping skills could mediate that. And it turns out that stress is mediated by coping, but support is not. So, got 10 minutes left. So, I'm pretty sure I was not going to be able to get to this. So, you can actually test this in multiple samples. So, the slides are still there. So, here's the model we were just looking at. Now the researchers wanted to know, was this different between males and females? And so here is the model for males. And you'll see it looks very similar to the model for the total population. That is, stress is mediated by coping. But it turns out in females, it's not. So if they hadn't broken the sample down into the two groups, right, they would be discussing findings based on the total sample, and that is, look, coping mediates the relationship between stress and anxiety and depression for everybody. But in their sample, it only did so for males. So that's sort of the end of my presentation.
This was really fascinating. A quick question and think some thoughts. I mean, when we do regression analysis or logistic regression or anything, we always talk about causal factors or factors that are in the causal pathway. And that's always a discussion or as to whether to include them into the regression or to exclude them or to stratify or doing things like that. So I guess that's a way of dealing with this causal pathway. This is great.
Yeah. I mean, its downside is, right, you need a large sample. Sort of the downside.
It's what?
The downside is you need a large sample size.
Right.
Yes,
Just a comment. That was really a great presentation. One of the areas that we could apply that where Deb and Thal were going to do it, but we never got around to it, was childhood obesity and all of the maternal and infant factors that might relate to that, and which ones are mediators and things that were in the causal pathway. One of the main one I think that she wanted to look at was breastfeeding, but of course there are a whole host of other factors that could be included in that. But this would be a great way to approach that kind of problem, that kind of question.
Any questions from?
Apparently, Stata 12 and 13 have SEM tools also, but bare bones.
I guess it's also an excellent way of looking at social determinants. I mean, that's basically what we showed there. So, social determinants or any type of outcomes, as a latent variable. I think.
Yeah, as opposed to using some sort of aggregate score.
Right.
Mm-hmm.
Right. That's great.
Yes, and I was going to mention that you can do this in Stata.
So which program do you use, Ryan?
So M+ is the only one I have access to on computer, so I'm using that one and R. But my dissertation I did R, EQS, and M+. So those are sort of the ones that I would use.
Great. Thank you very much.
Sure. Thanks.